I'm Terry Caliste. Welcome once again to Knowledge Base, the mathematically based show where we have fun doing math. And we're able to have fun doing math here. Why? You know it. Because here we're going to work smart, not just hard. We're going to develop a broad analytical repertoire. We're going to look at problem solving, mathematically speaking, from a variety of points of view. And we're going to give particular attention to my favorite kind of math problem. You know what that is? Word problems. Don't you love word problems? Sure you do. You just don't know it yet. But you will love them within the next half hour. For example, consider this problem. On the surface, it could boggle the mind. Notice what it says. What is the perimeter of a square that has the same area as a circle that has circumference 1? Now, let's use what we know. And in this instance, we're going to work our way backwards. In other words, we're going to work our way up to perimeter, the perimeter of the square. And first, we're going to start off with what we know, what concrete information we have. The circumference is equal to 1. Well, we're going to set it equal to 1. Why? Because we need to know what r is. Why? Because if we know what r is, we can find out what the area of the circle with circumference equal to 1. Why is that important? It's important because the area of that circle is equal to the area of the square. Who cares? We care. Why? Because if we know the area of this square and we can find the value of the side, we can multiply by 4 and solve this problem. Enough of that. Let's do the math. C, which is equal to 2 pi r, we're given that it's equal to 1. We're going to find what the radius is. In other words, we're going to divide both sides by 2 pi. And in doing so, we know this. We know that r is equal to 1 over 2 pi. You see that? Sure you do. It's trivial. But we have a long way to go. So, bear down. Now, we're going to find out what the area of that circle whose circumference is 1 is, right? Area is equal to pi r squared. But we know what r is. Do the math. Let's substitute. That's equal to pi times 1 over 2 pi, and of course, squared. Pi times r squared. Here's our r, and we're squaring it. You see that? Sure you do. Let's simplify. This becomes pi times 1 over 4 pi squared. You have to be careful. Most students forget that when you're squaring a fraction, in this particular instance, where there's a product in the denominator, we're actually squaring every factor. But you knew that. In this case, this becomes 2 squared, which is 4, and pi squared, which is just pi squared. But we can simplify here because we can cancel a pi here and one of the pi's down here, thus leaving us with the result 1 over 4 pi. That is the area of the circle. But now the area of the circle, whose circumference is 1, is equal to the area of the square. Let's set that equal. Here's what we have. S squared is equal to 1 over 4 pi. But our objective in this instance is to find out what the value of S is, the length of a side, right? Right. Take the square root of both sides. What do we get? The square root of S squared is, right, it's just S. And the square root of 1 over 4 pi, the square root of 4, you know, is 2. This becomes 1 over 2. What's the square root of pi? In this case, we don't have to bother with that. Why? Because we know it's just the square root of pi. Because look at the possibilities. You'll notice that it's very important to look at your answers. Look at our answers here. You notice they didn't simplify what the square root of pi was in either case, and neither will we. It's a waste of time. It might be cute, but it doesn't add anything to solving the problem. You notice we have 4 times the square root of pi, 2 over the square root of pi, 1 over 2 times square root of pi, 1 over pi, or just 1. So simplifying the square root of pi is, in this case, meaningless. Moving right along. We know what the side is, S. Now, we've used concept 1, 2, 3, and here's where we are. We know that we're trying to find the perimeter of the square whose area is equal to the area of a circle whose circumference is equal to 1. And we recursively worked backwards to find S. Now, it's just simple simplification because P is equal to 4S. And what's S? Right, it's 1 over 2 pi. So this becomes 4 times 1 over 2. Actually, it's the square root of pi. 4 and the 2's will cancel, thus leaving us with 2 over the square root of pi. See that? Take a deep breath. Exhale. Feels good, huh? Yeah, and you know why? Because even though there were a few steps involved here, I admit, we didn't panic. We identified the basic concepts that were involved in solving this seemingly difficult word problem. Now, let me recapitulate. The problem said we wanted to find the perimeter of a square whose area was equal to the area of a circle, and that circle had circumference equal to 1. So you notice we first identified the concepts, right? Then we related them to quantities that we had definitive information for. In this particular instance, we knew that the circumference was equal to 1. What did we do? We set it equal to 1, and we found R. Why? Because we needed R to find the true value of the area of that circle. In doing so, we substituted R, which is 1 over 2 pi, into the formula for the area of a circle, and then we simplified that. And then we set it equal to the area of a square because we were told that those two areas were equal. And in doing so, we found the value of the side, one of the sides of the square. That was important because we know that 4 times S is the perimeter. That's what we were setting out to find out all to begin with. And in doing so, we got the right answer, 2 over the square root of pi. You see, this is what we call being analytically agile. What does that mean? Well, we have the analytical agility such that we can actually work right through these concepts and not panic and not be intimidated and not be discouraged. Why? Because we're actually using a thought process that's related to concepts. You see, if students can identify concepts, the rest is trivial. Let's look at another seemingly difficult word problem, but you'll find by taking a methodical and a logical approach, trivial. I love this stuff, don't you? Sure you do. Now, have your thinking caps on tight. Consider this. A train started at station S and has been traveling R miles per hour for T hours. In terms of R and T, how many miles from station S had the train traveled 3/4 T hours ago? Did you get that? Now remember, we need to focus on concepts. In this case, the concept is D is equal to RT. In other words, the distance is equal to the rate of travel, times T, which represents time. And we want to know how far that train traveled from the station S, right, 3/4 of the time and hours ago. Now that's a mouthful. But here, let's identify what we know. We know that the total distance is RT, right? So from point A to point B is RT. That's our distance. And the question is very tricky because it talks about 3/4 of the time ago. So in other words, if we started here and ended here, 3/4 of that time ago means we're going to actually go back 3/4 of the distance. You see that? That was a tricky question, but not for us because we can relate what the word ago means. It means going backwards, right? So here we are. There's RT. See that? Now we want 3/4. We want to know where we were. How far did we travel? 3/4 of that particular time. So we're actually going back 1, 2, 3 out of the 4 quarters intervals. So in other words, we're actually going to subtract 3/4 of that distance. You see that? Boy, we got out of that one. Wasn't easy, but we were working smart. We were using the powers of observation. You see? Now, let's do the math. Because this, we know, is actually equal to 1/4 the distance traveled. Now it's simple. Can you tell what this difference is? Looking at the possibilities, it's RT minus 3/4 RT. Is it RT over 12? Or is it 3RT over 4? What do you think? Maybe it's just RT. What about 4RT over 3 or RT over 4? No need to guess. We're going to put our, in this case, arithmetic skills to play. For example, we know that the common denominator here has to be 4. We also know that the coefficient, that number in front of R, is 1. It's understood to be 1, but we don't write it because it's understood to be 1. But we can take that 1 and we can rewrite it as a number over itself. In this case, we're going to rewrite it as 4 over 4. You see that? Sure you do. 4 over 4 RT minus 3 over 4 RT. Why do we do that? Because we want to combine these two distances. Now you see it, don't you? Sure. Common denominator is 4. And basically we're saying 4RT minus 3RT. 4 of something minus 3 of the same thing leaves us 1 of whatever it is we're talking about. In this case, 4 minus 3 is just 1. 1 times RT. Whew, we got out of that one. You're taking this problem, you identify the concept, and more importantly, you recognize the value of understanding the meaning of the words that are given in that particular word problem. You can find the right answer just as easily as I can. You see that? It's trivial. Stay right there. We did it. Now, hope you have your geometric hat on. Take a look at this interesting geometric problem. This is like a breath of fresh air, isn't it? Yeah, because we love geometry. You'll notice we have two lines, L1 and L2, and they're parallel. See that? You'll also notice that they're both intersected by this particular line. In geometry, it's called a transversal. And there are very interesting relationships between angles when a transversal intersects two lines, particularly when those two lines are parallel, as in this particular case. For example, you'll notice that we have x is equal to the number of degrees in this angle, and this angle is equal to 2x minus 30. What is x? Notice the possibilities. What do we have here? 30, 50, 70, 105, maybe 210. What do you think? Can you determine, can you deduce by using the powers of observation? Some of you can. But now, here's how we're going to methodically solve for x so that it's crystal clear to all of us what exactly is the value of x. And we're going to do it by relationships. We know that this angle plus this angle under here, they're supplementary. In other words, if you add those two angles together, right, they're equal to 180. But now, those who have eyes will see. If these two lines are parallel, right, this angle, x, is also equal to this angle. You see that? These two angles are congruent. So they have equal measure. But now if that's the case, if x is equal to this angle, we also know that if x plus this angle is equal to 180, then the sum of this angle, which has the same value of x, plus this angle here underneath the transversal, 2x minus 30, if you add those two together, right, they're equal to 180. Let's do the math. X plus 2x minus 30, we're saying that's equal to 180. Right? Right. Now, combining like terms, x plus 2x is 3x. And we're going to take this 30, this minus 30, we're going to add 30 to both sides of the equal sign. It's called the additive property, or the additive property of addition, or the additive principle, whatever you want to call it. But be that as it may, we want to keep all our variables on one side and get all of our numbers on the other side of the equal sign. But you knew that. It's trivial. In adding 30 to both sides, this is what we get. 3x is equal to 210. See that? Now, inverse operations. Divide both sides by 3. X is equal to 70. There. You're taking a standardized test. You see these two parallel lines intersected by a transversal with these two angles given as such, x and 2x minus 30, and you identify those relationships that exist when given a transversal intersecting two parallel lines, namely, these two lines are supplementary, angles rather. Likewise here, and this angle and this angle, they're congruent, they have the same value. It's trivial algebra, and you're moving on to the next problem. And so are we. Stay there. Okay, get ready for this one. A square and an equilateral triangle have perimeters big S and big T, respectively. If little s and little t are the respective lengths of a side of the square and a side of the triangle, then in terms of their perimeters, what is little s minus little t equal to? What do you think? Now, did you understand the problem? Here's what we know. Ultimately, we want to find the difference between little s and little t. But we know that when we're dealing with the perimeters of a, let's say, a square whose perimeter is big S, right? What is that equal to? Well, a square has 4 sides. So this would be 4 times little s. You see that? The perimeter is equal to 4 times the length of the side. And they gave us a hint because they told us that we want to find the difference between little s and little t. You see that? You do now. Now, if you know this, you also know that big T, right, the perimeter of the triangle, is equal to what? How many sides are triangle? 3. Right. So it's 3 times the length of any given side. So in other words, little s is the length of the side of a square. Little t is the length of the side of the equilateral triangle. See that? Sure you do. But now, we need to find out what little s is and little t. Let's use our algebraic agility. We want to isolate s and t in this instance. So we're going to divide, in this case, both sides. I can make a better S than that. By 4. There. These 4s are going to cancel. Little s is equal to big S over 4. See that? Simplifies things, doesn't it? Likewise, here we're going to divide both sides by 3, and little t is equal to what? Right. Big T over 3. When we divide both sides by the numerical coefficient of the little t, 3. Now, let's do the math. S minus t, the lowercase. Here's S, big S, over 4 minus little t, which is big T over 3. Common denominator is 12. Do the math. In this case, we're going to cross multiply here, right? So 3 times big S is just 3 times the big S minus, sign doesn't change, 4t. See that? Look at the possibilities. They all seem to look the same, don't they? But a careful examination will tell us, there, that's the right answer, right there. The most commonly chosen wrong answer, by the way, is actually, well, either one of these two. Because what will happen if we're not careful, some students inadvertently rushing will actually add the denominators instead of multiplying to find a common denominator. In this case, the least common denominator, but not us, because we're working how? Smart, and not just hard. Let's look at another problem. Now, let's lighten up just a bit. Here we're dealing with quantitative comparisons. And on typical standardized tests involving quantitative comparisons, we have 4 choices. We can choose the choice in column A over here, which in this case would be X, if X is greater than what's given in column B. If B, in this case 27, is greater than whatever X is, and we're going to find out in just a second, by the way, then we would choose B. If those quantities are equal, right, we're going to choose C. And we're going to choose choice D if we do not have enough definitive information to determine a precise and unique answer. So now, let's evaluate the information that's given here, and let's find out what's greater, okay? You'll notice, in this case, we have a triangle, and we also have one of the lines extended here such that this angle is given to be 96. Is that important? Well, think about this. We want to find out what X is. Concept involved? Right, the sum of the interior angles is equal to 180 degrees. We have one. We want this one. We need to find out what this angle is. Think about another concept. We just used it, in fact, in the last problem. Supplementary angles, right? The sum of these two must be equal to 180. Well, let's subtract 96 from 180 and find out what this angle is. And then the rest is trivial. We have 180 minus 96, right? This is what? 84. See that? We're saying that this angle here is 84. Now, we know that 180 minus the sum of these two is X. Let's do the math. We have 57 and 84. This is what is this? 141. Here, we're going to subtract 141 from 180. Why? Because 180 minus these two is equal to X. So 180 minus 141 in this case is 39. You're taking the SAT examination, you're given this geometric diagram, and you're comparing that with X in column A and 27 in column B. You're going to choose column A every time if you take this approach using those concepts that we identified and employed. It's that simple. Let me show you another one. Okay, get those calculators ready. See if you're going to keep up. How many perfect squares do you know? This is what I teach my math clubs. around the country. Perfect squares. 1 squared is 1 times 1, right? Which is just 1. 2 squared is 2 times 2, which is just 4. This is 9, 16, 25, 36, 49, 64, 81. 10 times 10 is 100, right? 11 squared is 121, 144, 169, 196, 225 is 15 times 15. But you knew that. 16 squared is 256, 289, 324 is 18 squared, 19 squared is 361. Of course, we know 20 squared is 400. Keep going. You got the calculator going, don't you? 21 squared is what? Right. It's 441. 22 squared is 484. 529. This is 576. This is 625. 676. 27 squared is 729. 28 squared is 784. 29 times 29? Right. It's 841. And 30 times 30 is 900. Don't you love this stuff? Yes. Because it's trivial. You stick with the source, and you'll be able to do perfect squares just like this. And there's many other tricks that we can learn that's very useful in improving our, not only our ability to do well, but our appreciation for mathematics. Boy, time flies when you're having fun. But, as always, we can always have fun with the source, knowledge base, right here. This is Terry Caliste saying, until next time, see ya.
Твій поцілунок п'янкий, п'ю і хочу ще. До тебе йду через гріх, і сором не пече. І ніколи ти не пізнаєш, я не розкажу тобі, як вночі мою душу крає біль.